So welcome Rigny and Susanna and Alexi and Fanny and Stefani and Antonio and Diego. Thanks for coming. Let me share my screen and we will jump right to the quiz. Okay, so here is the quiz. And as hopefully you expected, the first question, at least, was determine if each of the following series converge or diverge. Show your work, state the tests you're using. All right, so we look at part A, and we have n equals 1 to infinity of sine squared of n over 3 to the n. All right, so let's look at A. And we need a strategy. What does this kind of look like? Is there a way to kind of get rid of something and clean it up? Anyone see? So what does part A kind of look like? Yeah, it looks like 1 over 3 to the n, because the important thing is sine squared of n, it's positive, and it's never bigger than 1. So that's the important thing, is that we know that sine squared of n over 3 to the n, let me write this out. I think I need to write it using an equation editor, otherwise it'll be too messy. So sine squared of n over 3 to the n. The important thing is when it's greater than 0, there's no problem with that. So that's kind of easy. And also, it's less than 1 over 3 to the n. Because remember that, 3 to the n, because the sine squared of n is never bigger than 1. So, and it's always positive because that's squared. So we're talking about a number smaller than 1 over 3 to the n is going to be less than, I guess I should say less than or equal to, but it doesn't matter because the test is going to allow for less than or equal to 1 over 3 to the n. Any questions on that piece? All right. We also know that the summation of 1 over 3 to the n converges. Why do we know it converges? So why does the summation of 1 over 3 to the n converge? Yeah, by the geometric series test. So by the geometric series test or GST, so you don't have to type the whole thing out. And therefore, by the, so what test am I using to get to my original series? Yeah, the direct comparison test, DCT, our series converges. Any questions on part A? Any questions? All right, if there's no questions on A, let's look at B. For part B, we have the summation n equals 1 to infinity 2n plus 1 over n squared plus root n. That's a complete mess. But what does it kind of look like? Yeah. If you look at the dominant term, it's basically n over n squared, or if you want 2n over 2n squared, but n over n squared. And n over n squared is 1 over n. So for B, okay, we're going to look at the summation of 1 over n squared. Now, hopefully you all know that the summation of 1 over n does that converge or diverge? It's an important one. It's the most important series there is.
Diverges.
Yeah, that diverges. And it's such an important series. It has its own test just for this one series by the harmonic series test. Comes up all the time. Okay, so that diverges. It's not obvious whether the R series from part B is bigger or smaller. That's hard to see. So if it's hard to decide whether it's bigger or smaller, then let's use a limit comparison test. And to use a limit comparison test, what we're going to do is we're going to look at 2n plus 1 over n squared plus root n divided by 1 over n. And what that does is multiply by n. So I think I need to put this into an equation editor. It's too messy otherwise. 2n plus 1 over n squared plus root n. 2n squared plus 1 over n squared plus root n. So you have 2n plus 1 over n squared plus root n. We have a summation. And then we're going to divide by 1 over n or multiply by n over 1. Remember, you could always multiply by the reciprocal. Any questions on that so far? Okay. And actually, we don't need the summation. We need a limit. Okay. And if I don't write n goes to infinity, it means n goes to infinity. That's kind of the way this class is going to go. If we don't write infinity, it means we're going to infinity. That'll just save a lot of time in writing for you and me. So now we go and do this. And this is equal to the limit of the fraction. We have 2n squared plus n over n squared plus root n. And then we're going to use a trick that I showed you last time, and that is multiply top and bottom by 1 over n squared. Okay, or divide top and bottom by n squared. And when you do that, we get 2 plus 1 over n over 1 plus, and if we take root n divided by n squared, you get n to the negative. And again, we have a half minus 2 is negative 3/2. Any questions on that? Okay, notice 1 over n goes to 0 as n goes to infinity. And so does n to the negative 3/2. Remember, negative means a 1 over. So I just get 2. Any questions at all so far? All right, so now we're ready to state our conclusion. By what test?
The harmonic series.
Yeah. Oh, I see in the
Limit.
chat box. Sorry, I see in the chat box. What did you multiply by? So I multiplied by n over 1. Is that what you meant? Oh, the last step? Oh, the second to last step. The second to last step, I multiplied by, oh, actually 1 over n squared. Sorry. There's a little issue there. There we go. But it makes no difference. You get the same answer. So sorry about that. So now we could say again, as you said, by the limit comparison test, or how about LCT? The series, let's write our series diverges. Remember, they always do the same thing when you have a limit that is not 0 and not infinity. Any questions on question 1? Any questions? Okay, let's move to question 2. And I decided to put some true false in. That gets you some practice with true falses. I think that's important because the exam, you've had me enough that you know that I give true falses on my exam. So expect them. So it's good to practice. So let's look at part A. So answer the following true or false. Prove your answers are correct. So if an and bn are both greater than 0 and n is greater than, for all n greater than 0, and suppose that the summation of an and the summation of bn both converge, then the summation of an bn also converges. What do you think? Is that true or false? Yeah, this one is true. But we need to explain now. We need to prove our answer is correct, which means state the theorem you're using and why it works. And the idea here is that, and you could pick either A or B, it doesn't make any difference, to pick which one you're going to be kind of adjusting. And maybe I'll do BN. So since the sum of BN converges, then BN must be less than or equal to 0, greater than or equal to 0, and it must be less than or equal to 1 for large n. Okay, actually, I don't need the equal for the 0 because I said it's greater than 0. Okay, and it must be less than 1, actually, for large n. Because if it's not less than 1, then it would have diverged by the divergence test. Any questions on that? So let me write by the divergence test, dt. Any questions so far? All right, so now what test can I use to look at the summation of A and Bn? Yeah, direct comparison test. So therefore, A and Bn is going to be less than An. Okay, and greater than 0, by the way. Because I told you everything's greater than 0. So by the direct comparison test, the sum of A and Bn converges. Any questions on part A? Okay, I want to emphasize, you'll notice that in all my proofs and all the explanations, I always state the test I'm using. Okay, and that is required. You must state the test you're using whenever you use a test. Let's look at part B. All right, so now if we have positive an and bn for all positive n, and let's suppose that the summation of an converges and the summation of bn diverges, then the summation of an over bn converges. True or false? Yeah, this one's false. And one of the things, hopefully you know by now, is that for true, you actually have to do a full proof with all the theorems and logic and all that. For false, there's an easier way to prove it. What's the easiest way of proving something's false?
Prove it diverges?
No, I like Adam's way. Find an example. All you need is one example that makes it not work, and it's false. And that's a proof. Do you remember that? That's logic. That's mathematical logic. Okay. To prove it using some kind of weird theorems, that'd be hard. Okay. So instead, it's a lot easier for false to just find an example. And the key, because I try not to be too evil. What's the most common series that diverges?
Anything equal to 0.
Now I want an example. Which special series diverges? Hint is we've already seen it today. Yeah, the harmonic series, not test, but just the harmonic series. Okay, so that's let Bn equal the sum of 1 over n. Any questions so far? All right, so now we want to find an an so that an time over bn diverges, where an converges. And the idea here is, again, we want to find something easy where it's easy to divide. So definitely polynomial makes sense because 1 over n is a polynomial. So I'm going to choose the easiest polynomial that we know converges. What's the easiest one? Let an equal, oh, sorry, not bn's not the sum. Bn is just 1 over n. So what's an? Okay, we can do geometric series, but that's going to be a mess when you start dividing and stuff. It's an easier one. Yeah, p series, but what p series? What's the easiest one that converges? Yeah, 1 over n squared. So 1 over n squared, and it's all going to work. Then an over bn is equal to 1 over n squared over 1 over n, which is equal to n over n squared, which is equal to 1 over n. Very basic algebra. So the sum of an over bn is diverges by the harmonic series, harmonic series test, because it is a harmonic series. Any questions on part B? So again, the key is find easy examples. Okay, I'm not trying to like do one that's just incredibly, amazingly impossible. You find the 2 easiest examples and they're just going to make it diverge. Any questions at all on the quiz? Any questions? Okay, if there's no questions on the quiz, let's move on. And let me ask you, are there any questions about anything else? Homework or some one of the tests we've been using and for convergence, something else? Okay. And while you're thinking, I want to remind you what I said 2 days ago about my schedule. And that is, do you remember what's happening on Friday?
Bruce is lecturing us because you have to interview somebody.
Yeah, Bruce is lecturing you. Don't be surprised when you see me there. Just want to let you know, I don't want you to be like scared. Because if I log in, then Bruce is there and doesn't have to worry about hosting it and all that kind of stuff with Zoom. So I'm actually going to be there. I'm going to have a computer and another computer next to each other. One is just going to be there so that Bruce can do the lecture, and the other will be my interviews. And I'm going to be on mute. I'm going to have it mute both ways. So you can't hear me, I won't hear you. So if you see me, that does not mean I'm listening or even seeing anything. It just means that I have my computer on so Bruce can go and do his thing, and hopefully that'll all work. Okay, because again, that way we don't have to go figure out a different link for you guys to go into for the lecture. you can go into the one you're used to. So it'll be the same link you're using now and you've always been using. And that way you'll be able to do that without having any issues. So again, don't be surprised if you see my name on Zoom, but that doesn't mean I'm looking at anything. Just a note, because I'll be interviewing someone. So that's a note. So Friday, I'm not going to be lecturing. I'm not going to be in office hours because I'll be interviewing someone while I'm in office hours. So no office hours. Sorry about that. Probably won't even be checking my email pretty much all day Friday. I do have office hours tomorrow night, tomorrow at 6 o'clock, but not Friday. Sorry about that. So that's one thing to note. And then Monday, I'm also not lecturing. How come?
Memorial Day holiday.
Yeah, Memorial Day holiday. So actually, you're not gonna see me again for a whole nother week after today. Maybe I'll make you happy. Hopefully not too happy, but you won't see me for a whole nother week. But just let you know. But I'll be checking my email, and I do have office hours today. I'll have office hours tomorrow evening, just not Friday and not Monday. And I'll be checking email here and there. I'm going to be gone for. I usually say I'll get back within 24 hours. That won't be true on Sunday, Monday, because I'm backpacking. I'll be off the grid. So don't expect anything back on from Sunday at probably 11 until Monday afternoon. I'll be doing the Memorial Day thing. So that's just a note. But then we'll be coming back Wednesday. There'll be a regular lecture Wednesday. And then a week from Friday, as I just saw Rigney talk, is there's presentations. And I just saw interested in doing a vector-related problem, which involves integration. If no one is called that yet. All right, the only problem, Rigney, is that integrating vector-valued functions is not this quarter. We haven't learned that yet. That's the Math 202 class. That's next quarter. So there might be some integration, but not integrating vector-valued functions because we don't know how to do that. That's beyond your knowledge, if you know what you've done in class and nothing too more. That's my only worry about integrating vectors. Okay, taking derivatives of vectors we know how to do. Dot product, cross products we know how to do. Gradients, directional derivatives, but not really integration. So I'm not sure. Maybe in office hours you can tell me what you're doing. So that's just a worry. That it'll be over your head. Okay. Yeah, stay for office hours. It's probably a good idea. Any other questions? Any other questions? Okay, if there's no other questions, then let's talk about alternating series. They're biggies, okay? They come up a lot. And they come up because a lot of times you go positive, negative, positive, negative, positive, negative. Can you think of some real world situations where if you watch something going on, it goes up and down and up and down and up and down? Can you think of some there's a lot of them. Okay, stocks are all right. I'd rather them go up and up and up and up. They tend not to go up and down and up and down. They tend to go up and up and down and up and up and up and down and down. So stocks turned out to be all over the place in terms of ups and downs. Temperature, okay. So temperature could work if you're looking at temperature because that mostly works because in the daytime it's warmer, nighttime it's colder. So if you're looking at some kind of ups and downs with temperature, that could definitely work. If you're looking over time. What else? There's another biggie in physics. Yeah, waves. Yeah, waves are the big one because waves are very consistent, up, down, always. Okay. And I want to remind you, I don't know how much physics you've had yet. I never know where you are in physics. Obviously, you know about waves in the ocean. But do you know everything in the universe is a wave? And have you learned about that? You are waves. You may not have known that, but it turns out there's waves in every particle. So that's a thing. It's called quantum physics. I'm just not going to get into the details of that, but there's waves going on there. There's waves when you hear sound, right? You've heard of sound waves, and those are waves. Light is a wave, even though it's just weird to imagine it being a wave, but light is a wave. So in physics, like everything is a wave, okay, once you get advanced. So that means that we need to deal with up, down, up, down, up, down, where it alternates going positive, negative, positive, negative, positive, negative. And a lot of times you want to find out what is the total sum. Okay, so what is the total sum with positives and negatives? Because if you're thinking about like going in the ocean, you got the force up, you got the force down, you got the force up. So what is the sum of all the forces as you let time go on, that type of thing. So I'm not going to get into the heavy details in physics, because that might even be too hard for your physics class, because that's more like at least sophomore level physics. Okay, sometimes higher, like junior. But I will let you know that waves happen a lot. Up and down happens all the time. So it's very important to understand alternating series, when alternating means up, down, but then you're adding up each of them. Any questions on the idea before I get into the definition? Any questions? Okay, mathematically, what do you know of that is positive, then negative, then positive, then negative? So in other words, if n is 1, if n is, say, 0, it's positive. If n is 1, it's negative. If n is 2, it's positive. If n is 3, it's negative, etc., etc. What can you think of an expression, a math expression, that has that property? Yeah, -1 to the n. So -1 to the n, definitely, if you start at 0, for example, it's positive, negative, positive, negative. If we start at 1, it's negative, positive, negative, positive. Okay. What if you want to switch where you start? So if you want when n is 1, you want it to be positive instead of negative, what could you do? It's a very small adjustment to the expression of -1 to the n. Yeah, -1 to the n plus 1. So now we're ready for the big definition. So I just kind of did that so that we can get our definition. Okay, so an alternating series. And again, this comes up over and over and over again in physics and mathematics, so it's a biggie. An alternating series is a series that can be written either as a summation -1 to the n times some bn, or the summation -1 to the n plus 1 times some bn, where bn is positive. Maybe I should write that down. Where bn is greater than or equal to 0. For all n. And by the way, whenever I say all n, that means all n that are defined. So if we're starting at 1, that means n1 up. If we're starting at 0, it means n0 up, wherever you're starting. Okay. Later in this class, I'll start at 2 sometimes. And that'll happen, believe it or not, that has to do with the second derivative. But just trust me on that one. Okay. Any questions on the definition of an alternating series? Any questions on this definition? Okay, easy to write examples. So here's a couple examples. And that is the summation n equals 1 to infinity, -1 to the n, over n squared plus 2. And the summation -1 to infinity, -1 to the n plus 1, over -1 to the n plus 1 times 3 to the 5n over n factorial. Do you agree that these are alternating series? Do they have the important things? Do they each have either a -1 to the n or -1 to the n plus 1, such that everything else is just positive? And if it is, it's an alternating series. Okay, let me give you another example. Decided to wait on this one just for fun. What if we had a summation n equals 1 to infinity? Of the fraction of the cosine of pi n over n. Is that an alternating series? What do you think? Okay, I see no. Well, let's take a look. Let's take a look. If n is 1, what do you get? What's cosine of pi times 1? What's cosine of pi times 1? Yeah, -1. So we get -1 over 1. What's cosine of pi times 2? Cosine of pi times 2 is 1. So we get plus 1 over 2. Cosine of pi times 3? That's -1. So we get minus 1 over 3. Cosine of pi times 4 is positive 1. We get plus 1 over 4. Do you see the pattern here? Is this an alternating series? Yeah, this is an alternating series. It's negative, positive, etc., etc. In fact, you could rewrite cosine of pi n as -1 to the -1 to the n. Okay, so again, just because it doesn't announce that it's -1 to the n doesn't mean it's not -1 to the n. Okay, what if we do the following? Let's suppose that let f of x equal 1 over n, 1 over x. Then let's look at the following series. How about the summation n equals 1 to infinity of f n of n? Is that an alternating series? And remember, f super n, that means the nth derivative of f and then evaluated at n. That's what that means if you forgot your calculus. Is that an alternating series? Okay, so yeah, if we look at this, the first derivative is negative 1 over x squared. The second derivative is positive 2 over x cubed. The third derivative is negative 6 over x to the fourth. The next derivative is going to be positive 24 over x to the fifth. And you'll notice that when you take derivatives of 1 over x over and over and over again, it goes positive, negative, positive, negative, positive, negative forever. And you're going to get an alternating series. So I wanted to give you some that like you look at this one, and if you just looked at it, you would say, that's not obvious an alternating series. Doesn't look like one. But then when you start working it out, you'll notice it is. And it turns out in the real world, these come up a lot. This one that I've got written, that's like one of the most important type of series there is. And we'll get into that in a few weeks. But I want to let you know, these are the biggies. So you're often going to be looking at series like that. Okay, we're going to have a series where it's a series of derivatives. And the derivatives, because you have a 1 over x or a 1 over something, each time it gets multiplied by negative 1. Any questions on this idea of an alternating series and what one is? Okay, so in the last week or so, what's our big question about any series? Yeah, does it converge or does it diverge? That's the question. Okay, because remember that if it diverges, don't put it in a computer and ask the computer to, tell you what it is, because it'll give you the wrong answer. It'll give you a number, and it might be, 183, and that meant it might have gone to n equals 1,000, and you got 183, except it diverges. It's not 183 because you're supposed to go to infinity, but computers can't go to infinity. On the other hand, if it converges, then if you let the computer go far enough, you're going to get a really good estimate. So it's very important to be able to answer the question, does it converge or does it diverge? Any questions on that idea? Okay, so for an alternating series, it turns out that it's actually really easy. Isn't that great? Don't you like easy? So this is one of the easiest tests we've got. And it is called the alternating series test. Not too surprising. I'll write AST because I don't want to write all the words every time. So the alternating series test, and it says, if you have any alternating series of negative 1 to the n bn or negative 1 to the n plus 1 bn, and if 0 is less than or equal to bn plus 1, which is less than or equal to bn for all large n, okay? By the way, that says we have a non-increasing sequence. So it means you never go up. You can go down or you can stay flat, but you never go up. And if the limit as n goes to infinity of bn is equal to 0, then the series converges. Any questions on this big theorem? Any questions? Okay, why does it converge? Why do you think this is true?
Wouldn't it be a direct comparison test, technically?
Well, what would you compare it with?
Well, no, I mean,
We'd have to have something to compare it with.
I think I was just thinking since bn plus 1 is less, and then or just bn is greater than that, and it converges, therefore it converges.
Yeah, but we don't know that the summation of bn plus 1 converges. Or bn. We don't know anything about convergence. We're hoping it converges, but with direct comparison,
okay, yeah, you're right.
Start with the convergence series. We don't have one. The key on this one is you look at it. I know this sounds weird, and it's easy to write it out. Okay, so I'm going to write out the following. And I'm just going to, it doesn't really matter whether it's an n plus 1 or n, because really, what is the difference between having an n plus 1 and an n? What's the only difference? How do you go from the to the n to the n plus 1? What do I have to do to these series? It's obvious. It's easy. How do I make that an n plus 1? I don't see you jumping in. You just multiply by -1. Okay, if I multiply this whole series by -1, then this n becomes an n plus 1 by the power rule, right? Because you get -1 times this is the same as -1 to the 1 times -1 to the n, and that's -1 to the n plus 1. So these series really are the same because multiplying by a constant, a non-zero constant, never changes convergence or divergence. We had that theorem at the very beginning. Okay, changing it to negative doesn't make a difference. So I'm just going to pick on the first one because it's less writing. And I'm going to look at -1 to the n times bn. Got it? Okay, and if I do that, okay, in fact, maybe I'll pick on the second one. It's a little easier to write. I'm going to pick on negative. That way I start at positive when n is 1. So if I do that, what I get is b1 minus b2 plus b3 minus b4. I'm not going to do this all day long. Hopefully you get the idea. Okay, that's what the sum is. And then we keep going. Dot, dot, dot. And then we're going to get to some big number. Okay, I'm going to do it by example, but my example works for any big number. So then I'm going to go plus b 1,000. And then minus b 1,001. And now I'm going to put in parentheses. Doesn't make a difference, but it makes it easier to see. And I'm going to actually put brackets here. And then I'm going to go plus b 1,002 minus, I want parentheses, b 1,003 plus dot, dot, dot. Any questions on that? Do you all agree that that's true? I can write that? Okay. Well, we know that this right here, the way I've written it, is going to be less than b1 minus b2 plus b3 minus b4 plus dot, dot, dot. And then it's going to be minus b999. Any questions on that so far? Is that clear? Okay, well, here's the thing. If I add the first 999 of them, I get some number. I don't know, call it capital A. It doesn't matter what you call it. I think I need to go here. It won't let me do it. There. Any questions on that? Okay, so you'll notice that this whole sum is bounded by capital A. All right, but I didn't have to cut it off on 1,000. I could have cut it off on 1,001. Let's do that. So I can now go and basically redo this whole thing. But I'm going to redo it the following way. I can go B1 plus negative B2 plus B3. Oops. And then plus negative B4 plus B5. Plus dot, dot, dot. So now the idea is I'm starting with B1. B1 is just some finite number. And negative B2 plus B3 is negative. Negative B4 plus B5 is negative. Do y'all see that? So now I'm going plus, instead of 1,000, we're going to be looking at 1,001 minus 1,002. But it's a plus here. And a negative here. And that's going to be, oops, try that again. Negative 1,003, 1,004. So pretty much what I'm doing now is I'm going to say, well, hey, now we know that it is bounded below. Okay, so this guy is going to be greater than some B. Because we're starting with B1. In fact, it's greater than B1 if I want. Any questions on that? All right, well, guess what? I looked at the partial sums, and I just showed that the partial sums are bounded below and bounded above. They're also, if we do two at a time, they're monotonic. If I do those two, then those two, and then add the next two, then they're monotonic. Well, if I have a bounded monotonic sequence, then I know it converges. Therefore, the series, alternating series, is bounded and monotonic. As a sequence of partial sums. Therefore, it converges. Any questions on the proof? So you just take two at a time, but you can look at starting with just two at a time, the first two, next two, versus grab the first one and then take the next two, the next two, the next two. And that changes kind of how you write it as bounded and monotonic. Any questions on that? Okay, so there's a proof. Now we can look at examples. So let's look at this one. Summation n equals 1 to infinity of negative 1 to the n over n. Okay, this one's really important. It has its own name. It's called the alternating harmonic series. So it's just like the harmonic series. It just had a 1 over n. But now we're going negative, positive, negative, positive. Okay. And in fact, usually, if we want to really call it the R, usually you put a +1 because we want it to be positive. That way we start positive. Does this converge or not? Yeah, this converges. Why does this converge? We take a limit. I think I can actually take a limit nicely. Yep. We take a limit as n goes to infinity. Of 1 over n, right? Which is the absolute value of negative 1 to the n plus 1 over n. When you take the absolute value, you're just getting rid of the negative 1 to the n plus 1. What is that limit? What's the limit as n goes to infinity of 1 over n? It's easy. It's one of the easiest nice limits. It's not infinity. 1 over a million is not a big number. Yeah, it's 0. Yeah, it's 0. Okay, so that limit is 0. So, and certainly this is our alternating series. So therefore, by the alternating series test, the series converges. Any questions so far? Okay, let's try this one. The summation n equals 1 to infinity of negative 1 to the n plus 1 e to the n over n squared. What happens when you take the limit as n goes to infinity of e to the n over n squared? Because the absolute value means get rid of the negative 1 to the n plus 1. If I plug in infinity, what do I get? What do I get if I plug in infinity? Okay, I get e to the infinity over infinity squared. That's infinity over infinity. When you get infinity over infinity, L'Hopital's rule. Derivative of e to the n is e to the n. Derivative of n squared is 2n. Plug infinity, I get same thing, infinity over infinity. Let's do it again. Use L'Hopital's rule again, but now the denominator becomes just 2. And now I plug in infinity, and I get infinity. Any questions on that? What can I say? What's the conclusion?
Series diverges.
Yep, diverges. What test did I use?
L'Hopital's harmonic.
No, there's no test called L'Hopital's harmonic. Good try, though. We actually have a test. Here's the hint. It was one of the very first tests we had.
Is it the divergence series test?
Yeah, just DT, divergence test. Yeah, just the divergence test. If the limit doesn't go to 0, then it diverges. Remember that? And our limit doesn't go to 0. It goes off to infinity. Okay. And taking an absolute value doesn't change going to 0, by the way. Okay. That's one nice thing about the divergence test is it doesn't care if it's positive or negative. You can take an absolute value. Any questions on why this series diverges? All right. So now that we have that, one of the things you want to say is that, like, for example, if we have the alternating harmonic series, we found out it converged, right? Sounds great. How do we decide what it converges to? Okay, just let you know this is not a telescoping series. It's not a geometric series. So you're not going to have a formula for it. That's anything you've ever seen before. But what we can do is we can say, well, we know it converges. Let's suppose that we're doing engineering and we only care about maybe a couple decimal places of accuracy. So how high up do I have to go so that I have that accuracy? Any questions on the idea? Whereas in the second example, it doesn't matter how you got, you're never going to get to infinity. So it's not even meaningful to talk about. But the first one, you can say, well, now that I know it converges, what should I tell my computer to compute this to? How high should I go up? Any questions on that idea? Okay. And here comes the theorem. And this is called the remainder theorem for alternating series. And it says the following: for any alternating series of the form -1 to the n, bn, or -1 to the n plus 1, bn, that converges by the alternating series test, then the remainder is less than bn plus 1. Isn't that beautiful? Isn't that so much easier than the integral remainder test? You don't have to take an integral. You don't have to do anything, really. It's just super easy. So let's do an example, and I'll show you how easy that example is. So how large an n do you need to approximate the summation n equals 1 to infinity of -1 to the n over n? So we're looking at a harmonic series, okay, the alternating harmonic series, with an error of less than 0.001. So I just go and use it. What is bn plus 1? So let's write this out. So our error, our remainder, is going to be less than bn plus 1. What's bn plus 1 in this case? Very simple. So it's bn plus 1. It's not 1. Good try. Okay, notice that in our series, bn is the part without the -1 to the n. So basically, you erase the -1 to the n plus 1, and that gives you bn. Now, we want bn plus 1. Doesn't make it that much harder. And what can we do? It's not supposed to be hard. Yeah, it's just 1 over n plus 1. Okay, because basically you take an absolute value, it gets rid of the whole -1 stuff, and then we plug in n plus 1. And then we want that remainder to be less than 0.001. Any questions so far? All right, and hopefully you're used to this in basic math, basic algebra. You take the reciprocal of both sides, and we get n plus 1. And when you take the reciprocal of both sides, the less than becomes greater than sign. Right? It changes the inequality when you take reciprocals. And the reciprocal of 0.001 is 1,000, Because remember 0.001 kind of read in words as 1,000th, and the reciprocal of 1,000th is 1,000. 1000. So what should we let n be? I guess I should have used capital N. Yeah, 999. Let n equals 999. And that'll do it for us. So then you go to your computer program and you do a little simple for loop saying let n equal 1 to n equals 999. And then you say, answer plus equals 1 over 1, negative, you go negative 1 to the n over n, and then it spits it out. Okay, believe it or not, that's all the code you need, and that does what we need to do. Any questions on that? Any questions? Okay, so the good news is, hopefully you agree the alternating series is actually pretty easy. Okay, these formulas are much simpler than the formulas we've had before. Integration is much harder than plugging in. Hopefully you agree with that, because alternating series remainder just means plug in n plus 1, and that's it. You don't have to integrate anything. Any questions at all? Okay, so now this is a definition, and it's an important one. Let's scroll down so I can get all in one line. There we go. So here's the definition. If we have a summation of an, then we say that converges absolutely if the summation of the absolute value of an converges. We say the summation of an converges conditionally if the summation of an converges, but the summation of absolute value of an diverges. Otherwise, we just say the summation of an diverges. So unlike our series where everything's positive, now there's kind of two types of convergence. There's absolute convergence and conditional convergence. And it turns out absolute is the best. It's wonderful if it's absolutely convergent. You have all kinds of wonderful things you can do that'll happen in a few weeks. Whereas if it's conditional, yeah, you can get a number, but there's all kinds of problems. So it just lets you know that. Okay, and divergence is always bad. So any questions on these definitions? Okay, so if you were asked, how does it converge or diverge? Then you look at it, and the first thing you do is you guess. And if you think it diverges, what test do you think we're going to use? Or what
DT.
test can you use, huh?
DT.
Yeah,
Right.
you can use, there's a few. Divergence test, that sometimes works. Another test for divergence that can work is you can use a comparison test to show it divergence. So if it kind of looks like a divergence series, then you could do a comparison or limit comparison test to show it diverges. So those are there aren't a lot of other tests you can use. Okay. So that's the first thing, is if you think it diverges, go right to it. Okay. If you think it absolutely converges, take an absolute value and use one of our tests for convergences. Okay. Number 2 turns out to be the hardest. Why does number 2 have to be the hardest? Why is it twice as hard as the others? Why is number 2 twice as hard? Yeah, you have two to do. You have to show an summation of an converges, and that's going to be involving a test and stuff. Then you have to start over. Okay. And by the way, if number 2 is true, what test is always the one you're going to use in this class, at least, to show an converges? to show the summation of AN converges, which is the only test you're going to be using. Here's a hint. It's the test we did today. The main test. It's the only one we defined today. Yeah. So we're going to use the alternating series test. So that's the thing. If you think number 2 is the right one, use the alternating series test. Do not use the alternating series test for number 1 because that does nothing for you. Okay, but it does give you that part of number 2. Then take an absolute value and use one of our many tests that we have to show the absolute value converges. So that's just a note, is that, there's strategies for each of these. So let's do some examples. All right, so determine whether each of the following series converge absolutely, conditionally, or diverge. And we have the summation n equals 1 to infinity of -1 to the n squared plus 1 over n to the 4th plus 2. And what I like to do is I like to just get rid of the non-dominant stuff. And I just focus n squared over n to the 4th. Constants don't usually matter. What's n squared over n to the 4th? It's not 1 over n. N squared over n to the 4th is not 1 over n. It was a typo. Yeah, 1 over n squared. Good. It's 1 over n squared. Does 1 over n squared converge? Yes. Okay, we didn't ever need to even talk about the -1 to the n to even talk about convergence. So my recommendation is first do it in your head quickly. And I just say, it looks like a 1 over n squared, that converges. So that means that it should converge absolutely, because I didn't need to use the -1 to the n. I didn't need to use the alternating series test. So instead, note that the summation n equals 1 to infinity of 1 over n squared converges by what test? What test gives us 1 over n squared converges? It's one of the easier ones. Yeah, that's the p-series test. All right, PST. So 2 is greater than 1. Hopefully you all know 2 is greater than 1. So we know that converges by the p-series test. Okay. This is one of those where it's not obvious which is bigger if you drop the 1 and the 2, the +1 and the +2. So if it's not obvious which is bigger, then go for the limit comparison test. So now what I'm going to do is I'm going to take the limit as n goes to infinity. And now I'm going to take n squared plus 1 over n to the 4th plus 2 divided by 1 over n squared, or multiply by the reciprocal. So I get n squared plus 1. Oops. Over n to the 4th plus 2 times n squared over 1. And that is equal to limit of n to the fourth plus 1, n to the fourth plus n squared, over n to the fourth plus 2. And then I can either use L'Hopital's rule twice, or I could divide by n to the fourth. You choose. Either way, I get 1. So what's the conclusion? We just use a limit comparison test. What's the conclusion? It converges. Notice, though, it's even better than that, because we took an absolute value when we got convergence, right? We took the absolute value. I ignored the negative 1 to the n. So I can say it converges absolutely. Any questions on that? Let's look at B. So now we have negative 1 to the n to the n over n factorial. What's your guess on that one? Always good to guess. So what's the guess? If it helps, let's just look at something, because I don't see you all guessing. I don't see anyone guessing. So let's take a look at something. I'm just going to look at this n to the n over n factorial. Maybe I'll pop in 10. So we get 10 to the 10, which is 10 times 10. This is going to get boring. Times 10. Maybe I'll do 10 to the 5th. Times 10 times 10 divided by, actually, no, I need more. So we have n to the n. Yeah, this is a mess. So let's go 5 instead of 10. It'll take all day long with the 10. So it's 5 times 5 times 5 times 5 times 5 over 5 times 4 times 3 times 2 times 1. What do you notice about this fraction? Is it big or small?
Wouldn't the numerator be larger than the denominator?
Yeah, the numerator is larger than the denominator, right? 5 times 5 times 5 times 5 times 5 is much bigger than 5 times 4 times 3 times 2 times 1. Okay, hopefully you all can see that. Okay, that doesn't change. I mean, if you have a big N, that much is going to be much, much, much bigger. So in particular, we know that n to the n, let's write this down, the limit as n goes to infinity of n to the n over n factorial is infinity. Okay, it's greater than 1 is all we really need, but I'll just remind you it is really infinity because the top is so much bigger than the bottom. Therefore, by the divergence test, the series diverges. Any questions on that? Okay, let's do this last one. You look at the last one, and if you ignore all this minor stuff, it looks like negative 1 to the n over n. Do you see that? part C? Okay, there's a 5 there over 5n, but the 5 is not important. So it's negative 1 to the n over n. It looks like the alternating harmonic series. So let's try showing it converges conditionally, because that one converges conditionally. So what we can do is we can take a limit. As n goes to infinity. And we ignore the negative 1 to the n. You get n cubed minus n squared. Oops, that 2 should be a 3. Over 5n to the 4th. Minus 3n plus 1. What is that limit? What is that limit? Hint, do L'Hopital's rule 3 times or divide by n cubed, whatever you feel like. Yeah, it's equal to 0. So by the alternating series test, the series converges. Are we done?
Larry, I have a question really quick.
Sure.
Are you taking the negative 1 to the n out because you're doing the absolute value, or do you always take it out?
Because I'm doing the absolute value. Whenever you're doing the alternating series test, the absolute value kills the negative 1 to the n.
Okay.
Does that make sense?
Yeah.
Yeah. So that's the whole point. We want to kill that negative 1 to the n. Okay. And the absolute value does that. Is it enough to say it converges? Are we finished? The answer is no. Okay. Because we're asked, does it converge conditionally or absolutely? Okay. I don't have time, but we can use the limit comparison test with 1 over n to show that it converges so that its absolute value diverges, because it's going to look like the harmonic series. Therefore, the series converges conditionally. Any questions on the idea? I know I'm going to kind of went through that fast, but you can imagine doing that, because I want to mention the last 2 theorems. There's not too much to do with them, but I want to mention them. This is a big theorem. And that is, if the summation of an converges, absolutely, then the summation of an converges. That's kind of immediate, right? Because if it converges absolutely, then that means that it's even better than regular converging. Does that make sense? So I'm not going to prove it, but it's true. And then comes a very strange theorem. And this is called the rearrangement theorem. And it says, let's suppose we have a conditionally convergent series. And let x be any real number. Okay, then there exists a rearrangement of terms such that the sum of the rearranged terms is equal to whatever number you want. On the other hand, if we have absolute convergence, then any rearrangement always gives you the same answer. So let me kind of show you what I mean by number 1 especially. So let's suppose we have the summation, the kind of the classic conditional convergence. Of negative 1 to the n over n. So that is equal to -1 plus 1/2 minus 1/3 plus 1/4 minus 1/5, etc. Okay, can I do the following? Can I just say that's equal to -1? And then I'm going to take -1/3 minus 1/5 dot, dot, dot. And then I'm going to go plus 1/2 plus 1/4 plus 1/6 plus dot, dot, dot. Can I do that? I rearrange the terms. Do I get the same answer? And this is what's weird. What you've been doing for the last maybe 10 years of your math career, you would say yes, but the answer is no. Okay, because what I did is I used a commutative property of addition by just switching the order of stuff. You could do that with addition, right? Wrong. When you have an infinite number of terms and you have a conditionally convergent series, you get a different number if you rearrange. Okay, and not only that, I could rearrange it in such a way I get 100. And then I could pick another way and get pi. Then I could pick another way and get -30. Whatever number I want, I can always get. Is that weird? But I'm out of time. So I'm going to stop the share and stop the recording.